Okay, welcome to Note Set 26A. Moving on into section 6.2, where we'll be talking about something called diagonalizing a matrix. This is something that pops up a lot in signal processing and control systems, networking, things like that. So lots of ECE content relies on this concept. I know I'm always saying that. Well, do you want to know why? Because first of all, linear algebra is a big, important tool for electrical and computer engineering, and I'm picking topics that are the keys to things that we're doing. So I shouldn't be teaching you things that you don't really need to know. So these are all important things. So I want to talk about how to adjust the water in the shower. Not an ECE problem, not something you were expecting to see me talk about here, but it's a great analogy that leads us into this idea of diagonalizing a matrix. So there's two common ways. You walk into the shower and there might be two knobs, a hot knob and a cold knob. And let's call X1 our setting for hot and X2 our setting for cold. And in this setting, maybe X1 and X2 are limited to be only positive numbers, but that's a small idiosyncrasy of this analogy, not what we're trying to do. Second way, I borrowed this image somewhere online. I'm not quite sure where. I probably should reference it, but it's a picture of a shower controller. So I don't really think I'm stealing anybody's intellectual property here, but yeah, I probably should have referenced where I found that, but I didn't. So we've got a little lever here, and what we can do is move that lever up and down in one direction. So we can move it along this way, and that actually controls the pressure. And we can kind of spin it back and forth this way, and that controls the temperature. Presumably, these things aren't perfect, but the intent is that you can adjust the temperature without changing the pressure, and you can adjust the pressure without changing the temperature. So these are two different ways to adjust things. But over here, note that when I turn the cold knob up, say, it'll get colder, but the pressure will also go up. So in some sense, over here on the right, things are decoupled. But over here on the left, the controls are coupled together. Or at least the impact on the output variables are coupled together. So I'm trying to control temperature and pressure, and I turn one knob and I will be affecting both of those. So let's look at this from a linear algebra point of view. Suppose I've got some matrix here. I've got my X1 and X2, so these are the numbers that I have control over. So we're still viewing things in terms of this transformation viewpoint rather than solving a system of linear equations. And there's some 2x2 matrix that is operating to map the X1 and X2 into temperature and pressure. And if we write out the equations for this, we can see that temperature depends both on X1 and X2, assuming that A11 and A12 are both non-zero. And the pressure will also be some factor of X1 and some factor of X2. So our system is coupled. Each input affects both outputs. Now let's look over on the other side. In that case, we have a diagonal matrix, and that's the beauty here. That's what we mean by a decoupled system. So if we write this diagonalized system out, we see that we get T is just equal to A11 X1 and 0 times X2. So there's no term here for X2. Likewise, we get 0 times X1 plus A22 times X2. So we just get A2, 2x2. There's no other term for x1. So pressure is directly controlled by the x2. Temperature is directly decoupled control by x1. So each input affects only one output. All right, so enough with the plumbing systems. But when we design our systems for electrical and computer engineering systems, diagonal matrices are beautiful. They lead to decoupled systems, so that when we're trying to design the system, we don't have to worry about, well, if I change this to get this effect, it will also change this other thing that I don't want to happen. So decoupled systems are a lot easier to analyze, and they're also a lot easier to design. Now, sometimes you're just given a system. You don't get to design it, but you have to design something to work with it. So, maybe you're given some complicated system, a car, for example, and you have to design an aftermarket cruise control for that. Or you're in the cruise control design system, but someone has designed the car already, and they say, okay, now you get to design the cruise control system for this car. The car may already be a coupled system. You don't get to design it to be decoupled for your purposes. But we can use mathematics to artificially decouple something. At least we can transform it over into an equivalent mathematical system that is decoupled, do our work in that, and then come back to the real world system after we've designed the decoupled system. So decoupling boils down to looking at diagonal matrices, and this idea of transforming into a diagonalized or decoupled system leads to the idea of diagonalizing a system. So is there some way, given some matrix that's not diagonal, can we somehow diagonalize it for the purpose of leading to a good design, simplifying design? Can we diagonalize the system but have it still represent the original system, and then be able to kind of come back to what we want to do? And we won't really delve into how this all relates to systems per se. You'll do that in your later ECE courses, but we're going to set the foundation, and it's all based upon eigenvalues and eigenvectors. So here's what we mean by diagonalization. You give me an n by n matrix, so we're still limiting ourselves to square matrices here. You give me n by n matrix, and one that has n linearly independent eigenvectors. So we've already talked about how the eigenvectors need not necessarily be linearly independent, but we're requiring that here. And we're going to put those into the columns of some matrix. We'll call it the eigenvector matrix. Makes sense. And for now, we'll call that matrix S. And since we have n linearly independent columns, S is going to be n by n, full rank, non-singular, so it's invertible. And let's take a look at the matrix S inverse times A times S. So we're basically hitting A from both sides, from the left with an S inverse and from the right with an S. And our claim is that the result of that will be a matrix that's diagonal, and we'll call it the eigenvalue matrix. And we've been naming our eigenvalues with the symbol little lambda. Yeah, you need to learn your Greek letters. They're good for more than just fraternities and sororities. Little lambda is what we've been using. This is a big lambda, uppercase lambda. So this will be a diagonal matrix, and the eigenvalues will be down the diagonal of that, and we'll have zeros elsewhere. And just pointing out here that if we do not have linearly independent eigenvectors, we cannot do this. So it's pretty crucial that we get those. So here's what we're talking about. If we take S inverse times A and then S multiply from the right, we'll get lambda. Lambda is a diagonal matrix. That means zeros are everywhere off the diagonal. And on the diagonal, we've got the the eigenvalues. And then the S matrix, we've got every column is an eigenvector. And those eigenvectors have to be linearly independent. Now, if we manipulate this, so we multiply from the right by S, we'll get rid of that and we'll get an S multiplying lambda. Multiply from the, I'm sorry, did I say right? Left. So multiply from the left by an S and we'll get a S lambda here, and multiply from the right by S inverse and we'll get S inverse multiplying lambda. So that's all on this side. But on this side, the S and the S inverse will cancel. And over here, the S and the S inverse will cancel. And we've isolated A. So we can undo the effect. And so this is a really neat thing. It says that you give me a matrix A that has linearly independent eigenvectors, and I can decompose it into this product of matrices, where the inside matrix is a diagonal matrix with eigenvalues down the diagonal. Boy, I'm getting a lot of ink there, so let me see if I can get rid of some of this stuff here. Come on. I don't know why it does that. There we go. Oh, that was troubling. And so this decomposition is called the eigendecomposition of the matrix A. And this process is called diagonalizing A. I do this operation to A and I end up with a diagonal matrix. So that's the diagonalization. We can also get this result, and I'll let you in on a little crude way to remember this. I can never remember which side the S inverse goes on for these two results. I just can't remember. But this one I can remember, and here's how I remember it. Like I said, it's a little bit crude. I look for this crude word right here. I'll not say it out loud, but there it is. And then I think of this as a hat. And so you say the crude word and hat, and you know that word. I remember that. And that will tell me that it's AS equals S lambda. And then from that I can get either one of these that I want. If I want A by itself, I know that I have to multiply from the left by S inverse, and I get S lambda S inverse. If it's lambda that I want, I know I need to multiply over here by S inverse to get rid of that and break lambda apart. So just remember the crude word hat. And then from there you can remember that. You don't even need to write it on your sheet of notes. Let's prove this one, because these kinds of ideas are pretty important, and by proving it we kind of see how it works and why it works. And it also kind of gets you up to speed on how to think about developing a new idea. Because when you're doing engineering, every once in a while you kind of need to be able to prove that this will always work. This is how it will always be. And you can't do that by just trying this case, it works. Trying this case, it works. Trying this case, it works. That's like claiming all odd numbers are prime. You know that they're not, but maybe you think they are. And maybe you think they are because you said, well, 1 is prime, 3 is prime, 5 is prime, 7 is prime. Yeah, see, they're all prime. Go one more. 9, not prime. Nope, not prime. So you can't just rely on showing a few cases. You can't even rely on showing hundreds of cases, although it does raise the possibility of it and raise the probability of it being true. But if you really want to know this is how it will always work, you kind of need to be able to work through some logic and math to show that. Now, the math may not really be describing the real world, so there may be some other issues that you haven't captured that prohibit it from always working, but at least you got a structure to work with. So we're going to start with S having as columns the eigenvectors. Then we're going to look at this product, AS. So here's AS. So there's A times a matrix that has all of the eigenvectors stacked next to each other as columns. And then, as we learned long ago, we're going to pass this A through, and it's going to multiply every one of these individual columns. So we now get a column here that's AX1, we get a column that's AX2, we get a column that's AXN. Okay, beautiful. But remember, each one of these is an eigenvector. So AX1 really becomes lambda 1 x1, AX2 becomes lambda 2 x2, and so on all the way out. All right, so that's one thing. Now we're going to look at the product of S times lambda. So notice that we're looking at the ASS hat part here, or AS is equal to S lambda. So let's look at the S lambda part. And if we can prove that these two things are equal to each other, then we've established that easy to remember result from which the other two results come easily. So let's look at S times lambda. So here's our S with all the columns. Here's our lambda, diagonal with the eigenvalues down. And now we're going to do the multiplication. And so if we look carefully at what is happening, this first column here will be lambda 1 times this first column plus 0 times the second column plus ... 0 times the last column. But since these are all zeroed out, all I get is lambda 1 times x1, and so that's the first column. Let me clear some of this off here. Then we're going to do this times all of these things. So it'll be 0 times the first column, lambda 2 times the second column, 0 times all the other columns gives us that one. And so we end up with this. And then, aha, those are exactly the same. Therefore, AS is equal to S lambda, and we have that. So we've established that AS is equal to S lambda, which is what we needed to prove. And then furthermore, since the columns of a square matrix S are independent, S inverse exists, and we can then form, we can solve for A and get A is equal to S lambda S inverse, or we could isolate lambda by S inverse AS. So that's our little proof of that. That wasn't too bad. A lot of these proofs go along the lines similar to that. They're not terribly complicated proofs. Let's take a look at an example, put some numbers in it. But, the number one thing that I hear from students is, I can only learn when I see things with numbers. Well, that's good up to a certain point, but engineering actually is not often about the numbers. You often don't have the numbers until the ideas are fully formed. So if you think engineering is just calculating with numbers, you ain't really seen what engineering is, to use some poor grammar there. Engineering is using the ideas to develop a structure that you think will solve a problem by meeting the requirements. And often you don't have the numbers until you're all done. You're driving towards the number. You don't start with the numbers. But anyway, here's an example with some numbers just to illustrate how it works. Because I know that does help you kind of see how this works. So here's our matrix. We can find the eigenvalues to be lambda equal to 1 and lambda equal to 6. And you can also find the eigenvectors to be 1, 0, 1, 1. So if we put all this together, here's our S matrix, and we need the inverse of that. Well, if we look carefully at this, this really is, it looks like an elimination matrix for doing reduced row echelon form, where we're trying to eliminate something above the diagonal. So we know what its inverse looks like. All we got to do is negate that one number above the diagonal. Or you could use any of the methods we've talked about earlier for finding the inverse. And so here's our A matrix, and we can multiply all that and find out that we get something that looks like this. So in other words, we're showing here, we showed that lambda is equal to S inverse AS, but if we did it the other way around, we could show that A is equal to S lambda S inverse. And so we're just alluding here to something that we'll be talking about as we go more into this. Suppose I wanted to know what A squared was. So this is kind of the advantage of diagonalizing a system this way. We can say, well, here's A, and here's A again. But notice that these internal ones actually become the identity matrix. And so now I get lambda squared on the inside. There's one lambda, there's the other lambda. They multiply together. And the only thing left on the outside is S and S inverse. So that's kind of cool. I have A decomposed this way. I want A squared. I just have to work on the stuff on the inside. And that's easy. Squaring a diagonal matrix, I would just square each individual element. You can check that lambda times lambda is just squaring the individual elements. So in general, powers of A, in this case, I can find easily any power of K. Any power of A. All I got to do is go in and raise the diagonal elements to the power. I don't show it here because 1 to any power is 1. And so now we can work that out, and that's what that thing looks like. Now you may wonder, so what? What's so big about powers of A? Well, powers of matrices show up in lots of models for modeling dynamic systems. So we might model some sort of complicated power system or a complicated control system, a financial system, any kind of networking system, a queuing system for networking. All of these kinds of systems can, when we model them as ECEs do, end up using powers of some matrix within the model. And we need to understand the behavior of that matrix as it's raised to an arbitrary power K. So I can't remember if it's at the end of these notes or another set of notes, but we'll be looking at a financial model for salary and savings that will illustrate how these powers show up. So I can't remember if it's in this set of notes or a subsequent set, but we'll get there. So 4 remarks about this diagonal eigenvalue matrix. Any matrix that has no repeated eigenvalues can be diagonalized. So that's nice. We then just have to wonder, well, when do we get repeated eigenvalues? And if we do, what do we do? How do we deal with this? If we can do anything at all. So let's keep our eye on that as we go through. We can multiply eigenvectors by any non-zero constants. So we've talked about that already, and that means that eigenvectors do not have a unique length, so we can make them be any length that we want. And so we often find it useful to normalize their length so that they are unit length. It just makes it easier to work with. The eigenvectors in S come in the same order as the eigenvalues of lambda. So let's back up here, and you can see that we had 1 was our eigenvalue that comes first. 6 is the eigenvalue that comes as the second column. 1, 0 is the eigenvalue that corresponds to 1, and 1, 1 is the eigenvalue that corresponds to, there's the eigenvector that corresponds to eigenvalue 6. And if we back up even further and go to the previous slide, which is completely cluttered with my messy ink, you can see that when we write this out, Well, I guess we'll go one slide even further. When we write this out, we've got lambda 1, we've got x1, lambda 2, x2. So the subscripts on the lambdas correspond to the subscripts on the eigenvectors. I guess that makes sense, and it should be obvious, but it doesn't hurt to state that explicitly. And then just a warning for when there are repeated eigenvalues. So up here we said with no repeated eigenvalues, we can diagonalize. The issue when there are repeated eigenvalues, it doesn't have to be this way, but for some matrices with repeated eigenvalues, they have too few eigenvectors. We don't have enough to do what we want, and it's those that we have a problem with to be diagonalized. So if you remember in that eigshow example, we had the case where as we dragged x around, we didn't get an ellipse. We got something that was a line. That's the case where that illustrates a case where we could not diagonalize that result. So here's another example of a non-diagonalizable matrix. If you remember, that example had 2 rows that were dependent. This has 2 rows that are dependent. In fact, they're identical. So if we work this out, we end up getting the determinant. We do the cross thing. We get something that looks like this. Work all that out. Some things cancel. We end up getting lambda squared. So our setting it equal to 0, we get lambda squared is equal to 0, and our eigenvalues are lambda 1 equal to 0 and lambda 2 equal to 0. So they're repeated. So now listen carefully. The fact that it's not diagonalizable is not because the eigenvalue is 0. It's because it's repeated, and it's not just because it's repeated and we only have one eigenvector. It's the same eigenvector for each of those 2 eigenvalues. So that's the problem. So if we solve for the eigenvectors, once we substitute into the a minus lambda I, one of our eigenvalues, and remember we plug it in and it's going to be the same. So from this equation, we need, we would like to be able to get 2 solutions to this equation. One for each of the 2 eigenvalues. But we can see that A has rank 1. It's a 2 by 2 with rank 1, so we know that the null space is going to have dimension of 1. So if you're confused as to how I'm getting that, go back and look at our discussion of the 4 amazing spaces, the 4 fundamental spaces, and see how we figured out the relationship of the dimension of the null space to the rank and the size of the matrix A. And if you go back and look at that, you'll be able to come back and say, oh, yes, a 2 by 2 with rank 1 will have a null space that has a dimension of just 1. So since the null space has dimension of just 1, there's only one solution to this. Or one vector that spans that. Every other solution is just a multiple of that one solution, and that's the idea of an eigenvector. So in this case, there's one and only one eigenvector, even though there are 2 but repeated eigenvalues. And again, it's not because the eigenvalues are 0, it's just because they're repeated. So repeated eigenvalues can lead to dependent eigenvectors, which would make the result not diagonalizable. I didn't quite spell that right, so I misspelled this here. It should be diagonalizable. So repeated eigenvalues can lead to this, but don't have to lead to this. So there's a lot to be puzzled out here as to when things work and when things don't work. And this is what I mean, that being an engineer is not just about give me the matrix filled with numbers, I'll calculate some numbers from it. We need to be able to understand when will this happen And when will that happen? So that when we do our design, we don't end up in scenarios that we don't want to happen. And you're not going to get there by just saying, oh, let me try it this way. Crap, that didn't work. Let me try it this way. Crap, that didn't work. No, you need to be able to drive your design exactly where you need it to go. And you need understanding to do that, not numerical answers to do that. Now, we've been talking about the invertibility of matrices, which leads to the concept of non-singular, tells us that the matrix is invertible. And now we have this new idea of diagonalizability. I spelled it right there, I think, diagonalizability. Okay, these two things are not the same, and there's not really a connection. Sometimes there's a loose similarity between these, but not really. And the reason is that the invertibility, as we'll see in a bit, actually is concerned with eigenvalues. So to check invertibility, it doesn't really have anything to do with the eigenvectors per se. At least that's not the primary thing. What really matters are eigenvalues, the values that the eigenvalues take. And diagonalizability has to do with eigenvectors, whether I have enough. We saw in the previous example that I should have 2 eigenvectors, but I really only had 1, and so that was not enough to get n, in that case 2, linearly independent eigenvectors in order to diagonalize. So we need independent eigenvectors to get diagonalizable. We need non-zero eigenvalues for invertibility. And to see this last bit, see, I put a colon there. That means that this stuff down here is something to do with that. So let's say that A is diagonalizable. So we've got linearly independent eigenvectors. So we can write this out this way. Then if all the eigenvalues are non-zero, then we can write A inverse is just the inverse of this side. And it turns out that ends up working out as S lambda inverse S inverse, which you can check if you just multiply all of this stuff, move it right up here, multiply away. You have the S inverse times the S, which undo each other. You've got the lambda times the lambda inverse, which undo each other. You've got the S times the S inverse, which undo each other, and you're left with the identity matrix. So A times this A inverse does give us the identity matrix. But what is that lambda inverse? Well, since lambda is diagonal, we know the inverse of a diagonal matrix is also diagonal with the reciprocals down the diagonal. Now, if any one of the eigenvalues is 0, then that corresponding reciprocal cannot be formed. But if all the eigenvalues are non-zero, then this reciprocal version is perfectly defined, and we have our lambda inverse, and everything works. So, invertibility has to do with, do I have eigenvalues that are not 0? So it's all about the eigenvalues. Diagonalizability is all about the eigenvectors. I can have repeated eigenvalues, I can have 0 eigenvalues, but the important thing is I got to have enough linearly independent eigenvectors to do the diagonalizability. So here's a result. Eigenvectors from different or distinct eigenvalues, not repeated ones, but distinct ones, are independent eigenvectors. So the eigenvectors x1 through xj that correspond to distinct eigenvalues are linearly independent. So the black part, the black ink just says the same thing that the red ink says in just a different way. And so what that leads to is an n by n matrix A with n distinct, that's the important point, eigenvalues has n independent eigenvectors, and thus it is diagonalizable. So let's prove this. We can't just throw these results out and expect you to believe them, but let's just do it for the j equal to 2 case. So what's j? We're talking about that these are all the eigenvectors that correspond to all the distinct eigenvalues. There may be some repeated ones, but we're not some repeated eigenvalues, but we're not counting those right now. We're only looking at the distinct ones. The non-distinct repeated ones, separate story. And so let's just look at the j equal to 2 case, and we can easily generalize this. So one method of proof is called proof by contradiction. So there's a joke among professors that another method of proof is in the classroom is proof by intimidation. So we just do it as quickly and as opaquely as possible, and the students don't have a clue. We get to the end and we say, there, we're done. That's proof by intimidation. Hopefully this will only be proof by contradiction and the ideas will be clear. So proof by contradiction, we assume the opposite of what we're trying to show, and then show that something that can't happen happens. That means that our initial assumption was wrong. Okay, so here's our assumption. We're going to assume that the two eigenvalues are distinct, but that their eigenvalues are dependent. This is the opposite of what we're trying to prove. So if we can go through and show that that assumption leads to something wrong, then this must not be true. Then that would mean that when the eigenvalues are different, the eigenvectors must be independent. So here we go. Let me clear off that ink if I can. I had to say it that way, didn't I? There we go. So since they are dependent, that means I can find a linear combination where C1 and C2 are not 0, such that the linear combination is equal to 0. So this little symbol here means there exists, or there does exist. So I'm saying since the eigenvectors are assumed to be dependent, then there exists non-zero coefficients. So C1 and C2 are, neither one is 0, such that this holds. Okay, good. Let me clear the ink off. So what we're going to do is take this equation here and multiply by matrix A. So when I multiply matrix A through here, I'm going to get an A times x1, which gives me lambda 1 x1. And when I multiply A times x2, I'm going to get a lambda 2 x2. So that's all I've done there. And I'm going to label this equation A, not because the matrix is A, just because it's the first one that I got to label with a letter. Now we're going to multiply star, same thing, by the scalar lambda 2. So when I multiply that through, I'm going to get something that looks very similar, but notice that I have different lambdas here. I have the same lambda here. So I'm setting up something that's going to give me some machinery to work with. So proving these kinds of things is different than what you might be familiar with. What I call the classic EECE plug, chug, and there it is. You just plug something into one equation, do a bunch of manipulations, and you get your final result. That's not what we're doing here. We have to be clever and set up something. So we've set up two things that are true, and now we can subtract B from A. So when we subtract the left sides, we get this. And we've used the fact that these two terms are the same, so when we subtract, those go away. We've also factored out the C1 and the X1, and we have the lambda 1 minus lambda 2. And over on the right side, 0 minus 0 is 0. So now we're getting somewhere. Okay, so here is the deal. Well, we assumed that the eigenvalues were different, so this term cannot be 0. And we always assume that our eigenvectors are actual non-zero vectors, so that can't be 0. So we've got some non-zero number times a non-zero vector, and we got to get a 0 vector. Well, the only way for that to happen is that C1 has to be equal to 0. And we can do the same thing, set this up a little bit differently, and end up with an equation that has C2 here. See if you can figure out what we would have to do up here to make that happen. And we would ultimately find out that C2 has to be equal to 0. So we assumed non-zero coefficients could get us this because of dependence, but it doesn't work. Therefore, the eigenvectors must actually be independent. This is a beautiful little proof. Pretty simple, but clever, and a lot of proofs run this way. So let's take a look at example of diagonalization and powers. So the book uses an example related to the Fibonacci numbers, which is kind of cool because the Fibonacci numbers, if you've never seen them, are actually pretty cool. And they lead to this famous thing called the golden ratio, which is pretty cool. But I thought it'd be more useful to think about a more practical example. It's not quite an ECE example, but you're going to be working, so you'll be earning a salary, and you'll want to retire at some point and send some kids to college maybe, or buy a house. So you're going to have a savings account or some sort of savings vehicle. So every ECE should have this, but it's actually remarkable how similar this problem is to a lot of things that are actually going on inside your phone or inside your GPS or inside your cruise control. All ECE things inside computer networks, all ECE things, and all of those things actually have systems that are modeled with equations very similar to this. So suppose you get a raise every year, 3%. We'll just assume you're not an outstanding employee, but you're getting the cost of living raise every year. So maybe that's because you were focusing on calculating numerical answers rather than getting the big ideas. And let's say that you've decided that every year you're going to put 10% of your salary into savings. Now, I didn't deal with issues of when you put this in over the year. So I'm just going to kind of imagine that every year you get this 3% raise at the end of the year, and at the same time you just take 10% of all your salary and plop it into your savings account. And at the end of each year they calculate 5% interest. So compounded annually, but not throughout the year. So a fairly simple model, but something that does represent what actually happens in many ECE systems. Now you're going to retire maybe say 40 years from when you start working. It might actually be a little bit later, a little bit longer than that. But let's just say after 40 years, what's your annual salary going to be, and how much saving would you have, assuming that you haven't changed any of this over the years, which you should, and you haven't spent anything out of your savings. Let's see if we can work this out. Well, we could just work out the year-by-year results, or we could write this down this way. We know that the salary in year k plus 1 is going to be your salary in year k times 1.03. That's the 3% raise. And the savings has no impact on your new salary, so this would get multiplied by the 0 to create this, which would be your salary in year k plus 1. But let's look at the savings. What's going into your savings? Every year you put 10% of your salary into savings. So 0.1 times your salary goes into savings for the next year. But you also get 5% interest on your previous year's savings. So your previous year's savings gets multiplied by 1.05 to capture the 5% interest. And so we can write this as a matrix formula where, I'll have to fix that. This should be U sub k, where U is this salary savings vector in the year k. UK plus 1 is the salary savings vector in year k plus 1. And here's some matrix A that holds the information about your raise amount, your investing amount, and your interest amount. Okay, so let's see what we can do with this. So assume we start at k equal to 0, the day you start working, we'll call k equal to 0. That's the 0th year. And suppose you started a starting salary of $60,000 and you just got out of college, so you've got nothing in the bank, so you've got 0 savings. And so, we can do everything in terms of thousands of dollars, so we can ignore the thousands, so that this is units of k. So there's our initial vector, u sub 0, and we could easily calculate what u sub 1 is. We just take u sub 0, plug that in, multiply by our matrix A, and we get that we now have $61,800 as our new salary, and at the end of that year, we've got $6,000 in our savings account because we put in 10% of 60,000. And we didn't get any interest on our previous year, so that didn't have any impact. And then we can go on. U2 would be equal to A times U1, so we would now be taking 3% of 61.8, and we would be taking 10% of 61.8 plus 1.05 of 6. But we could also plug this result in, A times U0, into here, and we get an A times an A. So that gives us the A squared times U0. And we could calculate what that is. And we could go on our merry way. And each time we would just say, well, if I want to know at U40 how much I have after 40 years of work, can I retire now? We could take our starting salary, take our A matrix, raise it to the 40th power, and multiply that. Now, you could be sitting around all day taking A times A times A times A times A. How do we find A to the 40th power in a simple way? Well, it turns out that we can use the eigen decomposition that we talked about to analyze this. So we can write A as S inverse times lambda times S. I just, actually, did I get it backwards? A, S, S hat. A is equal to S times lambda times S inverse. So I use my little nasty mnemonic to figure that out. And again, I've been trying to tell you we are not about calculating numbers. Well, sometimes we are, but that's not the main thing we want to do. We want to know, how does this work? What kinds of things might I want to tweak? So we really want to look at this for an arbitrary K and see how our savings and our salary changes with K. And we might want to explore what happens if I change the amount I put away each year, or what if I do a different investment vehicle, or what if I work harder so that my boss is impressed and gives me a better salary increase each year. How much is that worth? How much will it change the behavior of the growth of my money? That is engineering. That's what we want to do. And this math will help us understand that. So we want to know u to the k is equal to a to the k, u sub k is equal to a to the k times u0. But we know that a can be written as s lambda s inverse. And we've already argued that when we raise this to the power, what really happens is this diagonal matrix in the middle gets raised to the kth power, and the s's just stay as they were. And so just recall what we did for the squared case, and you can see how it works. Notice that the s inverse and the s inside end up annihilating each other, and you get a lambda next to a lambda, so you get the lambda squared. So that's why that works. So to analyze how this system works, looking at the eigen decomposition of this, finding the eigenvalues, and looking at the eigenvalues raised to the kth power, because that's what's happening in this lambda to the k. It's going to be the eigenvalues raised to the kth power. That's the beauty of using this eigen decomposition. So let's take a look at that. We find the eigenvalues of this. And for this problem, it's very easy to find the eigenvalues, largely because there's a 0 sitting here. And so the multiplication in that direction gives us 0. So we really just have this times this. So we have two nice factors. When we set that equal to 0, it's very easy to find that it's these diagonal elements that give us the eigenvalues. And we kind of knew that already. We said that for a triangular matrix, the eigenvalues are, oops, I have an error here. This should be 0.1. So you might want to fix that in your notes in case I don't remember to fix it. So for a triangular matrix, the eigenvalues are along the diagonal. And we see that we do indeed find that here. So to find the first eigenvector, we would put in lambda 1 equal to 1.03 into this matrix, and we get this. So we want to find the vector x that is in the null space of that. We see that that matrix is a 2 by 2 with rank 1, so we know the null space will have dimension of 1, so there's going to be one vector that satisfies that. Again, its length is arbitrary, so I just picked an easy one, an easy version of it, 1 and -5. It's not unit length, but it has nice simple numbers. To find the second eigenvector, I plug in lambda equal to 1.05 into this matrix, and I get something that looks like this. Again, we see a 2 by 2 with a rank of 1, so my null space has a dimension of 1. So I should get one eigenvector, and if we solve that, we can see that that one is a valid eigenvector. Again, I can multiply that x2 by any number that I want, but this is a simple one, and that one does have unit length. So there's my S, and again, this looks like it's an elimination matrix, so we can immediately figure out what its inverse looks like. So we've got those. We put all that together, and here is our a to the k. So we have something that looks like this. And for a savings account and a salary, we want these things to grow. This is going to be what contributes to the growth of our money. For other systems that we want, engineering type systems, we typically want those things to decay because we want our system to, after we stop putting stuff into it, we would like it to decay away, its response to decay away. Sort of like a slinky, once you get it bouncing, once you get it oscillating, it will eventually, if you don't move it anymore, keep your hand still, it will come to rest. So for financial systems, you want them to grow, but for other things, like control systems, you would like them to settle down to some steady state solution. So there's our solution if we work all this out. That's what our a sub k, or our a to the k, looks like. And now we can play around with seeing what this looks like. And if we wanted to change our values here, 1.03, 1.05, 0.1, we could go back and redo this and come up with another version of this to see how things will change as we change those. And if you are really slick, this would be real engineering, write these values of A. Let me clear some of this ink off. Write them out arbitrarily. So write this as some number, alpha. Write this as some other number, beta. And remember, this is really supposed to be 0.1. Write this as some third number, gamma. Or you could even write this as 1 plus alpha, 1 plus beta, to keep the 1 characteristic. In that case, alpha, beta, and gamma would all be numbers less than 1. And then you could solve this problem symbolically. There would be no numbers in this, not a single frickin' number anywhere in this. And you would be trying to get down to the point where you could understand what does the impact of alpha, beta, and gamma have on how fast my money grows. So if I wanted to tweak one of those, and I could only devote resources to make one of those tweaks happen, which would be the best one to tweak? That is engineering, well, financial engineering in this case. But that's the kind of thing that engineers do. And notice there were no numbers involved in that. It was all thinking about concepts, all thinking about variables and symbols. So you have to strive towards doing that because that's what engineering is about. So finally we get this result, and we can then say with my initial salary we had no initial savings in here, we can figure out equations for what those things are, and we can easily plot those as a function of k. So I didn't do the plot versus k, but you could do that to see how these things grow for these particular values. So I'm hoping that this provides some insight into, first of all, what engineers do, how engineers do it, and kind of the thinking of engineers, but also the fact that without, kind of before you know it, you write down a model for how some engineering system works, and more often than not, suddenly you're going to see eigenvalues and eigenvectors popping into the picture here. As I said, this is not just a way of studying savings plans, but many types of engineering systems end up looking like this. So the book gives some more details on this kind of stuff if you're interested. So here's another example of powers of A. We've mentioned something called a Markov Matrix before, where the sum of the columns add up to 1. This is used to model probabilistic systems where you're moving from one state to the next with a probability depending upon which state you're currently in. And we had previously found the eigenvalues and the eigenvectors of that. And now we can decompose this way, and we can easily and very quickly find what a to the k looks like. And here we see that since one of our eigenvalues is 1, that won't change. And our other eigenvalue is less than 1 in magnitude. And so as k gets bigger and bigger, that entry gets smaller and smaller and smaller. And eventually, this column will go to effectively 0. And so we can figure out that in the long run, as k goes to infinity, this element becomes 0 here, and when we multiply all this together, we get something that looks like this. And that actually tells us something about, in the long run, what's the probability of certain states occurring. So we use this kind of analysis to figure out not just what's the probability of going from this state to that state, but what is the general probability of this one state ever occurring overall. And so when you're analyzing these kinds of probabilistic systems described by Markov matrices, eigenvectors and in particular eigenvalues really come into play to analyze these things. So when all of the eigenvalues are magnitude less than 1, and then we look at the power as k goes to infinity, it goes to a 0 matrix. So that's kind of an important result that shows up in a lot of engineering scenarios. Networking, modeling probabilistic processing like facial recognition, speech recognition, autonomous cars, control systems, flight control, all that kind of stuff gets modeled this way, and these kinds of results allow us to understand how things behave. Now, we did mention earlier that some matrices just are not diagonalizable using the techniques that we've been talking about so far. And we've seen that this can arise when we have repeated eigenvalues. It doesn't have to, but it can arise. We'll see an example in a little bit where we have repeated eigenvalues, but still we can diagonalize. But it can happen. And that's really, if we don't have repeated eigenvalues, we've already proved can't happen. We can always have diagonalizable matrices then. But this leads us to the discussion of multiplicity of eigenvalues. So most eigenvalid one more time, most eigenvalues are not repeated. And we would say that we would call those simple eigenvalues rather than repeated eigenvalues. And we would say the multiplicity is equal to 1. So if we have a non-repeated eigenvalue, there's going to be a single eigenvector associated with it, and it defines a line in the space, the n-dimensional space in which we're working. And then, so if we have all non-repeated eigenvalues, we'll end up with n different lines, n different independent eigenvectors, and therefore the eigenvectors end up basically being a basis for our space. But sometimes eigenvalues are repeated. And we have to talk about how do we count its multiplicity. Well, the obvious way is to just, I should have done the algebraic multiplicity first. The obvious way is to just count the repetitions of lambda. And we'll call that algebraic multiplicity, or AM. It's just the number of times it's a root of this equation. So if we had something that was like, lambda squared times lambda minus 1. Now we have 0 repeated twice and 1 repeated once. So the algebraic multiplicity of 1, eigenvalue 1 would be 1. The algebraic multiplicity of the eigenvalue equal to 0 is 2. Now the geometric multiplicity is what captures when we can and when we cannot diagonalize a matrix. So we've already said it's not just the repeated eigenvalues that cause the problem. It's repeated eigenvalues open up the possibility, and for geometric multiplicity, we just count the number of independent eigenvectors it has. And so this is the dimension of the null space of that. And so this is for a given eigenvalue. So in this case, we would plug in 0, and we would check the dimension of the null space. We don't have to plug it in twice. We just plug it in once, and we know, there's 2 of those eigenvalues. The most I could have is 2 independent eigenvectors. I might only end up with 1. The dimension of the null space might be 1, but the dimension of the null space could be 2. In this case, it's going to be one or the other. So here's an example. So if A has one eigenvalue that is repeated 3 times, then there could be some other ones, but this multiplicity is for a given value of an eigenvalue. So that eigenvalue, the number 4, has an algebraic multiplicity of 3 because it happens 3 times. It has a geometric multiplicity of, I don't know, could be 1, could be 2, could be 3. Can't be bigger than 3, can't be less than 1. But it could be any one of those, and I don't know from just knowing the values of the eigenvalues. I'd have to know the whole structure of the matrix. So here's an example. Repeated eigenvalues with the geometric multiplicity less than the algebraic multiplicity. So here's a pretty stupid looking matrix, 0, 1, 0, 0. But this is the classic example for this scenario. There are others, but this is the simplest one to see. So let's take a look at it. Take a look at our determinant of our A minus lambda I. Pretty straightforward. We take lambda, well, minus lambda times minus lambda gives us lambda squared minus 0. So lambda squared, set that equal to 0, and we have 2 eigenvalues that are repeated. Lambda 1 is equal to 0, lambda 2 is equal to 0. It's not because they're 0, it's because they're repeated. Okay, so just make sure you understand that. Now we look at our matrix A minus lambda I, plug in lambda equal to 0, because that's the eigenvalue that we're looking at, the value of the eigenvalue that we're looking at. This term goes away for this case, and we're left with just A. So this has rank 1. null space is dimension n minus k. Well, n is 2, k is equal to 1, so we're left with 1. So my null space has a rank of 1. That means I should have 2. That's the maximum that I would have. That would make my geometric multiplicity equal to my algebraic multiplicity, but I don't. I just get 1. There's only one eigenvector that is shared between these two repeated eigenvalues. So the algebraic multiplicity is 2, but the geometric multiplicity is 1, and that's a crappy case, not diagonalizable. Here's an example of one that has repeated eigenvalues with the geometric multiplicity equal to the algebraic multiplicity. Well, this is a projection matrix. We've already looked at this, and we've already talked about how projections have eigenvalues that can only be 0 or 1. And remember, we looked at that graphically in the last set of notes. But we set this up algebraically now. We look at our determinant. We get something that looks like this, and we can see that we have, once we set this equal to 0, we get lambda equal to 0, lambda equal to 1, and lambda equal to 1. Those are our only options, and the ones will, well, both of them could get repeated, the zeros and the ones, but not in this case. So now we have 3 eigenvalues, 2 of which are repeated. So 0 has a geometric multiplicity and an algebraic multiplicity of 1. The value 1 has an algebraic multiplicity of 2. Let's find out its geometric multiplicity. So we plug in lambda equal to 0. Well, we're doing the other one first. We get this matrix. We can see that it has rank 2. So n is 3, so 3 minus 2 gives us 1. So there's going to be one eigenvector corresponding to that eigenvalue. And there it is. You can verify that that actually works. So that's good. One eigenvalue, one eigenvector. That's perfectly what would happen, what should happen. But now let's look at the troubling case when we have repeated eigenvalues. So we could end up with one eigenvector between these two, or we could get 2. We don't know yet. We have to check. So let's take a look. So now we plug in our lambda equal to 1. Let's go back up here. So we would get a 0 here, a 0 here, and a minus 1 here. So we plug that in. There's our matrix. Now we see this has rank 1, but the size n is 3, so we're going to have 3 minus 1. I didn't fix this. Gives us 2. I better fix that. So now we have 2. That tells us that the dimension of the null space is 2, so we should have 2 eigenvalues. 2 eigenvectors that are shared between these 2 repeated eigenvectors. And we saw that before when we looked at the projection matrix. We drew a little plane. We showed 2 independent eigenvectors spanning that plane, and that's the idea. So, in fact, any vector in the projection space, so in this case we're projecting down onto R2, so any vector that has its first 2 elements non-zero and its last element 0 is an eigenvector. So we can pick any 2. So since we can pick any 2, let's pick them to make them independent. Then we can diagonalize. And in fact, why stop at just making them independent? We can make them orthogonal, and we can make them orthonormal. And we should if we can. Why should we make them orthonormal? Well, remember that we often need to find the inverse of our eigenvector matrix. And when you make them orthonormal, you get an orthogonal matrix for your S matrix. And finding the inverse of that, easy as can be. Just transpose it. We've talked about that before. So x1 is orthonormal to these 2. Why is that? Oh, we talked about that already. because it lies outside the projection space, and the only thing that will project to 0 is something that's orthogonal. So we've talked about that already, so go back and look at the last set of notes. And so there's our two vectors, and we chose them to be orthonormal. And so now for this eigenvalue, the geometric multiplicity is 2, which equals the arithmetic multiplicity. And when the geometric multiplicity equals the arithmetic multiplicity for every eigenvalue, then the matrix is diagonalizable. Now, something interesting here. This is our last slide. So what about eigenvalues of a plus b and a times b? Well, in general, the eigenvalues of the product AB, I screwed this up, are not, I'll have to fix this, are not the eigenvalues of A times the eigenvalues of B. And the eigenvalues of A plus B are not, I'll have to fix that, not eigenvalues of A plus the eigenvalues of B. So it doesn't work that way. And that's one of the challenging things when working with matrices. You know the individual eigenvalues, but you can't figure them out easily for things like sums and products. All right, so that's the end of this set of notes. I will make these changes, I hope I remember them all, in the notes before I convert them into PDFs and post them. And we'll see you in the next set of notes.